decent yet. And anyway, that might help you follow along a little bit.
Okay, Misha, you can start.
Yeah.
Wait, let me do the screen sharing. Let me see if the screen sharing works. Do you see that okay?
Yeah. So are we ready to start?
Give me 1 second. Okay, I guess so.
Okay, everyone. We are happy to have Neitzke from Yale, Moscow now. Well, giving talk about spectral networks and related stuff. Yeah, thanks.
So thanks a lot for the invitation. I'm really sorry that I can't be there in person, and I hope that I'll have the opportunity soon. So this is part one of 2 or 3 lectures on kind of introduction to spectral networks. And the aim is to be rather informal and relatively on the pedagogical side. So so this is not the kind of seminar talk where I'm supposed to say a lot of things you don't understand and you're supposed to kind of maybe figure it out later. Ideally, if I say something that you don't understand, it'll be better if you just stop me right away and we can talk about it. So in other words, I feel it's supposed to be a little bit more like a course than a regular seminar talk, and so it'd be nice if we treat it that way. At least that would be better for me. So let me give you some rough sketch of what the plan is. So I'll make a little diagram. So at the center of the story is going to be a construction that I call path lifting. That's connected to various kind of interesting subjects in geometry, such as the WKB analysis of ordinary differential equations, Donaldson-Thomas invariants, numerative invariants, particular ones that are called Donaldson-Thomas invariants, very specific examples of Donaldson-Thomas invariants. Cluster algebras, I guess cluster algebras and cluster varieties, so maybe I'll just write clusters. So all these things, you know, they're all their own independent subjects, but I want to think of them as all being kind of influenced by this construction of path lifting. This path lifting construction is something that organizes, in some sense, the 3 of these things. And in turn, those 3 things are all related to the hyperkähler geometry of moduli spaces of Higgs bundles. So I'll just write hyperkähler geometry. Which is, at least for me, the most exciting application of the construction. Let me also list another recent thing on the side, since I'm just drawing these pictures, which is that this path lifting also turned out to be connected to quantum topology, like the construction of like the Jones polynomial and relatives of that. So the main thing I want to explain to you then is what is this path lifting construction, and you know, how does it get applied to all these different things? Now, path lifting itself is in some sense a totally topological thing, but it looks unnatural if you just introduce it as a totally topological thing. So the way at least the way I want to get it, is to start with some very specific object, which is called the WKB spectral network. well, that's what we called it. It had more or less appeared earlier as the Stokes graph. And so that's going to be kind of the flow of these lectures. Today, I'm just going to define this object called the WKB spectral network. And I'll kind of beg you to believe for a day that this is going to be something interesting. This is going to have applications that will be developed in the following lectures. Okay, so that's the rough plan. And so the kind of mathematical story that I'm going to tell, the way I'm going to tell it along the lines of some joint work that I had with various people. So it's an account of it's at least closely connected to joint work with various people. So my collaborators are Davide Gaiotto, Greg Moore, Lotte Hollins, and then for some of the more recent parts, Fei Yan and Dan Fried. And it's connected to mathematical and physical ideas of many, many people. Let me just mention a few people whose ideas are kind of particularly prominent here. So a lot was motivated by the ideas of Kontsevich-Soibelman, Fakh-Goncharov, for the Higgs bundle stuff, Nigel Hitchin and Simpson, Carlos Simpson. For WKB, this all turned out to be connected to this theory of exact WKB, which is developed by Voros, Ekal, and many others. Okay, so this is far from a complete list. Okay. Anyway, so let's just start. So as I say, today this is just going to be a construction where you start with some very simple data, and you build an object. So we'll start with, so today is basically WKB construction of the WKB spectral network. So okay, so here's my data. We'll take a compact Riemann surface. An integer, at least one. And this integer, okay, the data is literally an integer. The way you should think of it, kind of informally, is that that integer is really standing in for the Lie algebra GLN. So this is part of a story which, in its full glory, you could try to develop the semi-simple Lie group, or at least for any ADE type Lie group. But it's simplest for GLN. So let's just talk about GLN. So in practice, we won't see the GLN appear directly. We'll just see the N appear. And then the last datum is a tuple, phi vector. So it's a bunch of objects on the Riemann surface, phi 1 up to phi n, where phi I is a meromorphic section. Meromorphic section of the canonical bundle to the ith power. In other words, in local coordinates, phi I would be written as like some function fi of z dz to the I. In other words, it's an abelian differential, a quadratic differential, a cubic differential, and so on up to an nth, an n differential. Each one being meromorphic. Now, this phi1 is not too important. So all the rest of them are important, but phi1 is somehow not that important. So we'll often simplify, just to simplify the statements and notation. It'll be convenient to just take phi1 equals 0. And so you could, in this story about a Lie group, you could think of that as being, we really do SLN instead of GLN. And so the case, you won't be surprised to hear that n equals 1 is basically trivial. On the other hand, the case n equals 2 is already interesting. So then, the tuple, since I said I'm going to take phi1 to be 0, then this tuple is just the data of a meromorphic quadratic differential. And so that's the simplest case to have in mind. Is we're just talking about a surface with a meromorphic quadratic differential, or it's a surface quadratic differential and a cubic differential. Basically, those two cases cover most of the interesting phenomenon that at least they'll talk about today. Okay, so that's the data. So we're just going to start with that, and we're going to do some geometric construction. We're going to make something. Okay, so what are we going to make? So let me start with spectral curve. So there's one kind of standard thing you can do with this data, which is to make the spectral curve. Remind you about that.
Sorry.
Oh, I got a bad echo there.
Yeah. Whether you put any restrictions on the orders of the poles?
So right at this moment, I don't want to put any restriction. In particular, right at this moment, it could be that there are no poles, that they're just holomorphic. Now, at some point, so I'm going to make a construction which you can define it in that level of generality. And then what will happen is that the thing you get will be incredibly complicated unless you put some conditions on the orders of the singularities. But I'd rather push those restrictions back to a little later, if that's okay.
Okay, yeah.
Okay, yeah. So what's the spectral curve? So now I'm going to assume I've got these data, and then the spectral curve is just given by an equation. So it's sigma. I'll write it sigma sub phi to emphasize the dependence on phi for a moment. It's given by an equation which is just sum grow up to n of phi I y to the n minus I equals 0. So it's an equation in the cotangent bundle of C. So think of this y as like a coordinate in the cotangent fiber. And phi I are our differentials, which live on the base. Well-defined equation, which defines some curve sitting inside of the cotangent bundle to the surface. Except I should say, so we had a tuple of differentials, phi 1 up to phi n. So in writing this equation, I just make the convention that phi 0 is equal to 1. So for example, when n is 2, and again, and phi 1 is 0, this just says sigma phi is given by the equation y squared plus phi 2 equals 0. So it's the Riemann surface of the square root of the of your quadratic differential. And so it would have, generically, it would have two sheets, which are just the two square roots of that quadratic differential. The square roots of a quadratic differential are naturally cotangent vectors, and so that's why this thing lives in the cotangent form. So it's a similar thing in general. So in the situation when sigma phi is smooth and reduced, which is what happens generically. So if you pick your phi, what will happen is that the spectral curve will be a nice smooth reduced curve. And then we can think of the projection. So we have sigma phi mapping to C. The projection is just a branched n-fold cover. So you know, there's C. Maybe sigma looks like this. Sigma phi. And it's branched over some, discrete subset. So the discriminant locus of this polynomial equation. We have a polynomial equation in Y. Generically, but sometimes it has fewer. When it has fewer, those are the discriminant points, and I'll use delta C for the discriminant locus on the curve. I guess it should be delta C phi, but we can't write everything. Okay. And so the ramification doesn't have to be simple like I wrote it here, but it'll be so just convenient to restrict to the case where the ramification is simple. And so I'll say sigma phi is simple. If it's, first of all, smooth and reduced.
The discriminant also depends on the set of phi's.
Yes. Yeah, sorry. Yeah, so I mean, you're right. I should really write it like this.
Sorry, maybe it's easy, but I don't understand. So how in sigma phi we have y's as unknowns, but phi's are fixed already, yes or not?
Yeah.
And why we are in cotangent space? What do we do with cotangent vector?
I mean, this is an equation. How do I say it? So
maybe tangent vector.
No. If y, think of it this way: if y is the name of a point of the cotangent space.
Okay. I see. Y is just okay.
Yeah, we shouldn't think it's the coordinate. It's kind of it is the point of the cotangent space. Okay, so we'll say that sigma phi is simple if it's first of all smooth reduced, and all ramification points are of index 1. So that's like what the picture that I drew here. The sheets only come together in pairs. Okay. And again, so in this basic case, when n is 2, sigma phi is simple if and only if the quadratic differential phi 2 has only simple zeros. Right? In that case, we're just talking about the Riemann surface of the square root. So then the ramification, yeah, in that case, simple is actually not an extra condition. The only condition is that it be smooth reduced. and it's smooth reduced exactly when all the zeros of the quadratic differential are simple zeros. And so sure enough, for a generic quadratic differential, it only has simple zeros. So in that sense, that's kind of the generic condition.
And what about poles?
For the poles, we don't put any condition. Yeah, but so we don't try to compactify this surface by extending it over like that. So if there's a pole, then the surface doesn't have any, the fiber over the pole is empty. Okay, fine. Okay, so from now on, I'm not always going to write the phi. So I might just write sigma, but it's always the sigma which depends on phi. Okay, so now I'm going to have to draw a lot of concrete pictures as we go on. So how am I going to picture this cover? I'll picture it in the following way. What I'll do is I'll choose a local trivialization of the cover. Choose a local trivialization of the cover. So I can't do it everywhere, but I can do it over some simply connected. I can always do it over any simply connected domain. Because there's no monodromy over a simply connected domain. Sorry, of course, then I should delete the ramification. Simply connected domain away from the ramification. So, what does that mean? It means I literally identify, I make a choice of a way to identify the components of pi inverse of u. So pi inverse of u will have n connected components, which are just the n sheets of the covering over u. I just identify that, choose the bijection with the set of integers from 1 to n. So in particular, there's a kind of maximal choice, which is to take u. I want to take u to be kind of as big as I can. Well, as big as I can is I draw a branch cut emanating from each point, from each point of the discriminant locus. I take u to be the complement of the branch cuts. So branch cuts emanating from each point of the discriminant locus. So let me draw a picture of what that's like. So, I mean, a kind of typical example of what some patch of this thing might look like is maybe you have, say, 3 of these branch points, and then from each one, you draw a cut. And then each cut is labeled with a permutation of the sheets, which says, if you're on one sheet, sorry, let me just write it first and then explain it. So maybe it would look like this. This one's labeled with the transposition 1, 2, this one 2, 3, this one 1, 2. It means if I follow a path, let me draw a path now. So now I'm drawing a path on the cover. So the way I indicate that path is, so sorry, let's be a little clearer about what's going on here. So this picture is drawn in the base. And if I want to represent an object on the cover, what I do is I draw its projection to the base, and then I fill it with a number which tells me on which sheet the curve is lying. So I'm drawing a curve on sigma now. If I label it with a 2 here, that means that it's on the second sheet. And so then let me try to draw a closed curve. So I'm drawing a closed curve like this. Along, of course, to be continuous, change sheet, so it's on sheet 2. When it goes across this cut, well, the curve just continues. Its projection is just this smooth, unbroken curve that I'm drawing here, but the label changes when we cross the branch cut. So this part of the curve is on sheet 1 rather than sheet 2. Then as it goes through here it crosses this cut, but this cut, sheets 2 and 3 are interchanged. Sheet 1 isn't affected at all, so it's on sheet 1 here. And then when it comes back to the left, it crosses this cut and goes from 1 back to 2 again. So this is a picture of a closed curve. This is a representation of a closed curve on sigma, but drawn on the base. So those kind of pictures will be convenient for us. Okay, so this picture curve on sigma. Okay. So that's going to be kind of our notation. And when sigma is simple, so we said that we're often going to impose this condition that sigma is simple. That's equivalent to saying that the permutations on the cut can be taken to be just transpositions. And so in particular, I don't have to put a little arrow that tells me which direction the permutation goes, because it's its own inverse. Because it's its own inverse, I can just draw it like this. Okay. Okay. Now, so what are we going to do? So far, all I've done is I've introduced you to the spectral curve. What are we going to do with the spectral curve? We're going to introduce some kind of interesting foliations of the surface. So let's get to that. So this is going to be, in the case of a quadratic differential, we're going to recover, I'm going to tell you something which will recover a very well-known foliation associated with differential. And the new thing will be in the higher rank situation. But okay, let's just set it up in general. So, so let's start with, suppose you have any Riemann surface. A Riemann surface S with a nowhere vanishing holomorphic one form rho. So suppose you have that data. I want to say there's a foliation of the surface associated with that data. Well, what's the foliation? Well, okay, so we have the distribution in the sense of a subbundle of the tangent bundle, which is the kernel of the imaginary part of rho. That's imaginary part, not sorry, right? It's not the kernel of the image of rho. It's the kernel of the imaginary part of rho. And so that's a one-dimensional foliation. So it integrates to give a foliation. Sorry, it's a one-dimensional distribution. So it integrates to give a foliation F rho on S. And that foliation is oriented. Let's draw a picture.
Is
Sorry, I
there,
can't hear.
is there a such a thing as a no vanishing holomorphic one form on the Riemann surface?
Nowhere vanishing holomorphic one form. Yes, that's what I said.
But if the genus of the surface is greater than 1, then there are no vanishing holomorphic one.
Oh, that's true. I didn't say S is compact. In a minute, we'll have the zeros. So the point is, you get a regular foliation, you get an honest foliation away from the zeros. And so for a minute, you should think that S means your compact surface with the zeros deleted.
Okay.
But then we deal with the case of.
Okay. Yeah.
Okay. So it's oriented by real part of rho. So let me just say what I mean by that. Yeah, so the picture is going to be, you know, a foliation. I just mean, you know, foliation in the ordinary sense. It's going to be an oriented foliation. So for example, you know, essentially the local example, if S is the complex plane, and rho the one form dz, then F rho is just the foliation by horizontal lines oriented to the right. Right, that's the kernel of dy. Being in the kernel of dy means it's a horizontal line, and dx being positive gives you the orientation. So okay. And by the way, F minus rho, if I reverse the sign of the one form, it just reverses it's the same foliation with the opposite orientation. Okay. So now suppose rho, we allow rho to have some zero. Then we make the exact same definition, but now we get a singular foliation. So if rho has isolated zeros, then the same construction gives a singular foliation. And so let me draw pictures of what that singular foliation looks like. So around the generic point that's not a zero, it looks just like what I drew before. Around a first order zero, you get a picture like this. These should be hyperbole. I'm not drawing it very well. And at a second order zero, you get a picture like this with 6 wedges. And let's see, let me try to draw also the orientation. So let's see, so it's like this, 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 it's like that. So this is around a regular point, first order zero, second order zero, and so on. Okay. Okay, so if you have a surface with a one form, you get some singular foliation of the surface. And a little more generally, suppose we fix. Then we can define another foliation just by multiplying the form by a phase. So I take my one form, the foliation F rho theta will be F, not for the one form rho, but for e to the I theta rho. A holomorphic one form and naturally gives you the circle's worth of foliations. Okay, now what are we going to use this for? We're going to use this not on our surface. On our surface, we don't really, on our base surface C. On our base surface C, we don't have a one form. We're also not quite going to use it on the spectral cover.
For an arbitrary theta, the singular points of the foliation will be the same. Yeah.
The zeros. Yes, yes, absolutely. Absolutely. That's right. So here, this point and this point, those are and yeah, this regular point. And yeah, so this is a picture of a neighborhood of each one, and these pictures are accurate, even conformal. So by conformal transformation, you can turn the picture into exactly one of these pictures. Well, a better drawn version. Good. Other questions?
No, that's fine.
Okay. Okay. So we want to use this. We want to apply this not to our original surface, and unfortunately, not even to the spectral curve. So we're going to apply it. Well, I think let me first say sort of loosely what we want to do. We want to apply this to the one forms. Say, I'll write them lambda I minus lambda j. Where, okay, so let's introduce lambda is the standard Leibel one form. So just the standard one form bundle to C. We'll actually never use it on the whole cotangent bundle. We just want its restriction to sigma. So we have the spectral curve, and the spectral curve has this totally canonical one form on it, the Leibel one form. But we don't want to, as it turns out, we don't want to use that one form to make a foliation. Instead, what we want to do is to take the difference of the values of the one form on two different and pull them down to the base, make a one form there. So lambda I is pullback of lambda from sheet I. So locally, what we can think we're going to do is we've got locally n different one forms that we get from the n sheets of this covering, and we're going to subtract them in pairs, and then we're going to make these foliations. You can describe the whole story that way, and sometimes I've done that, and it's always confusing. So I'm going to try something different this time, which is to do it globally on the place where it makes sense. And the only thing about that is that the place where it makes sense, it first sounds like a slightly funny thing. So now let's construct the place where this construction makes global sense. So let's make a definition. Let's define the root curve.
And indeed the pullback or push forward.
Well, I guess it's the pullback, right? You have the section. So you have locally. I mean, of course, they're diffeomorphic, so you can kind of say it either way. But I think one way to say it is that you know, over the patch U, you have n different sections of this covering, and what you're doing is you're pulling back the form through the map.
Yeah, I see. Yeah.
That's why we needed cuts.
Given by one. But anyway, okay, this is, if you like, some heuristic understanding of what we're about to do. But now I'll do it. I'll say it slightly differently. So let's continue. So let's assume that sigma, which is sigma phi, is smooth. Then let's define the following thing. Sigma twiddle. Let's just write it first. So it's going to be all the points in sigma cross sigma where their image under the projection is the same. So it's like the fiber product of sigma cross sigma, fiber product over the base C. So that's a fairly nice canonical thing. Now, though, I want to delete the diagonal. So that's sitting inside of the cotangent bundle. And now I want to take the closure. And we'll call that the root curve. So what is this in practical terms? All it means is it's the covering whose point. Yeah.
How is it sitting inside the cotangent bundle?
Oh, why did I say it's sitting inside the cotangent bundle? No.
Not the square of the cotangent.
Yeah. It was sitting inside of the cotangent cross the cotangent. I take the closure there. Yeah, thanks. Sorry. Yeah, so various people have tried to convince me over the years that it's a good idea to use this, and I always resisted it until this time. So let's see if it worked. And I think who just asked that question?
I did.
Was it
Benedict?
Who's I? Yeah, it's Benedict. Right. So Benedict is one of the people who tried to convince me to use this thing.
So can I actually comment that I use something slightly different, which is the Camarel cover, which is a cover of this.
Right. So I'm still resisting using that, at least for this discussion. Okay, we'll see. You know. Let's see how it goes. So anyway, so this thing, so what is it? It's the covering whose points now are just pairs of points. You know, a point of this covering is like two sheets of the original covering. Okay, so this is smooth. So it's now an n squared minus n sheeted covering. Branch cover. Let's see. Because you know, we had an n sheeted cover, we took its fiber product with itself, so we got n squared sheets, and now we delete the diagonal. So okay, so for example, for n equals 2. So for n equals 2, this is not a big deal. In fact, for n equals 2, this is literally another language for talking about sigma. Yeah, sorry. So I wanted to introduce the projections. So we have sigma twiddle. It has first and second factor. So I'll call those P1 and P2. And then, of course, those are both mapping down to C. And so in general, that's a kind of non-trivial diagram, but for n equals 2, P1 and P2 are both just isomorphisms.
Because one point determines the other, it is just the other. Yeah, and we just take out the branch points. So sigma.
Нет, там стало написано руками. Ну, туда продолжать все, что я тоже.
Is it okay?
Yeah.
So it's again revified cover, yes?
Branch.
Branch.
Yeah, so in this case, you know, the sheets of sigma, if you like, we have C, and then sigma has two sheets that are labeled, say, by 1 and 2. And then sigma twiddle, its sheets are supposed to be labeled by pairs. But what are those pairs? Well, one of the pairs is the pair, and the other one is the pair 2, 1. And so, of course, there are sort of two natural bijections between sigma twiddle and sigma. There's a bijection where you take the first element and the bijection where you take the second one. So that's all this is. But for n equals 3, of course, it's already different. So then sigma twiddle to C is a 6-to-1 covering. Well, sigma to C is a 3-to-1 covering. And P1 and P2 are branch double covers. Sigma twiddle to C. Okay. Okay, so we're gonna work on this root curve because that's where everything kind of makes global sense. Everything that I want to talk about. Now, but nevertheless, for drawing pictures, we'll trivialize.
Hang on. Why is P1 a double cover?
Oh, sorry, triple. Thanks. What did I do wrong here?
Oh, wait, it is double for n equals 3. Okay, yeah.
Oh, yeah, no. Okay, good, thank you. Good.
But this is particular to n equals 3. Sorry.
No, absolutely. This is for any example. Yes. Okay, so to represent paths on sigma twiddle by pictures, I'll do just like before. I'll choose a local trivialization. And if I have the same picture I had before, I'm going to say 1, 2, 2, 3, 1, 2. A path on sigma twiddle will be, again, you represent it as a path on the base, but now it's labeled by a pair of sheets instead of just one sheet because it lives on this double cover. And that the labels will get transformed as you travel along the picture by the cuts. Maybe we could have one that ends at the branch point. So that's a picture of how you might represent the paths kind of concretely. Okay. All right. So that's the root curve. So whenever you have a spectral curve, there's this canonical other thing, which is the root curve. And now, finally, we can introduce the foliation. It's going to be interesting for us. So we're going to have a canonical form on the root curve, which is just this. We have these two projections, P1 and B2, projection on the first factor on the first sheet and second sheet. And what we'll do is we'll pull back the standard 1 form by both of those projections and subtract them. And that gives us a globally defined 1 form on this root cover. So this is just the global way of saying what I said informally before. You take lambda I minus lambda j. This is the global version of that. Okay, so this is a so it's a holomorphic 1 form on sigma twiddle with only over the branch points. away from the branch points, from the explicit form of the Liouville one form, which is kind of, y dx, right? You see that when the sheets are distinct, the difference of values on different sheets will be non-zero. So this is a holomorphic one form on sigma twiddle, which has zeros only over the branch points. And so we get a foliation now. We said whenever you have a holomorphic one form, you get a foliation. So we'll get a foliation F rho, or more generally, we could twist it by this angle theta of sigma twiddle, with singularities only over the branch points. Okay. And since this rho is absolutely the only one form I will ever use on this cover, on this root curve, and so sometimes I'll just write this foliation F theta. Okay. Okay, so now I'm going to start drawing pictures of this foliation. And there's one fact that's important for our life, which is that we have an involution, of sigma given by mu of x and y is y and x, right? Just reversing the two factors.
Sigma tilde.
Sigma tilde, thank you. It's also a typo in the, thank you. That one reverses the sign of this rho. It just exchanges P1 and P2. And so with respect to this foliation, what that means is it preserves the leaves of this foliation and just reverses their orientation. So it preserves the leaves of F theta for any theta and it reverses their orientation. Okay, that's roughly going to mean we only have to draw half as many foliations as we might have thought. Okay. Okay, so I hope it's at least clear that maybe the formulas look a little abstract, but I hope it's clear at least I've defined some foliation root curve. And now I want to show you some pictures of what it's like in practice. So for example, so let's do the simplest case. Let's do the case when n is 2. So when n is 2, first of all, our cover sigma was just a double cover, and sigma twiddle was also a cover. So sigma twiddle to C is double cover. And moreover, this involution mu, in that case, actually is just the covering involution. Right, we have a double cover, you have the involution just exchanges the two sheets. That's what this mu is in this case. So what that means is that this F theta, which is an oriented foliation of the cover, it descends to an unoriented foliation downstairs. The leaves are invariant under the involution. That means they descend to leaves downstairs, but without a canonical orientation. So F theta descends to an unoriented foliation of C. Well, with singularities, so we said the singularities are going to be over the branch points, of the covering. So the singularities will be at the branch points. That's the branch points is what I called delta C before. It is at delta C. And remember, in the case of a quadratic differential, delta C is just the zeros of the quadratic differential. So just the zeros of the quadratic differential. So what do those singularities look like? Well, if you work out what the singularity is upstairs, if you figure out the orders of the zeros and so on, it turns out that what you had upstairs is this 6-pronged thing that I drew before. It corresponds to having, z squared dz upstairs. And so downstairs, we're quotienting now by this, we're quotienting that picture by Z2. And so what you get is a 3-pronged thing downstairs. So the picture looks like this. So this is the picture around a simple zero. So this is the picture of the foliation. So this is on C now, around a simple zero of phi 2. There's this kind of 3-pronged structure. And so if you assume that all the zeros are simple, then you just have these kind of 3-pronged singularities, and that's all you have. Well, to be exact, that's all you have. Phi was holomorphic. Now, the case that we typically want is actually the case where phi is meromorphic. And so we should say what happens around the poles. So if our quadratic differential was meromorphic, then, then f theta, you can think of it as being a foliation of the whole surface, but with some singularity at the poles. And what those singularities look like, so then it depends on the order of the pole, but here's the kind of typical pictures. So let's write what will happen for various things. So like, you could have a simple pole. You could have a double pole. For the double pole, what happens depends a little bit on the residue. So let me draw the pictures for a few different cases. And this is all with theta equals 0. Otherwise, multiply everything by a face. And then there's the case of a higher order pole. So now let me draw the picture. So a simple pole is actually the sort of dynamically trickiest one, because what it does is, or let's say dynamically most useless one, it just has one line. There's exactly one leaf of the foliation that ends up on the pole. If you have any other leaf, it just kind of goes around like this. So okay, fine. So a simple pole is in some sense almost invisible. But once you start having higher order poles, they tend to kind of attract the trajectories. So like the typical behavior. So if the residue is some random number, the typical behavior, the trajectories kind of spiral in. That's for a second order pole. Yeah, this one's hard to draw. Draw a couple of them kind of spiraling in. And then, for one particular phase of the residue, they just go straight in. And then for one very unlucky phase, they make like they make these closed loops. So that can happen. And then if you have a higher order pole, it again kind of attracts the leaves, but it attracts them, instead of attracting them kind of isotropically, it attracts them in some specific directions. So like there will be some n directions, kind of asymptotic rays going into the singularity where the trajectories are going. So this was for a singularity of order n+2 of the quadratic differential. There's kind of n asymptotic directions. So here I drew 3. Okay, so that's what this foliation is like. It's a regular foliation of the surface, except that it has some singularities at the zeros and poles of your. Okay, so it'll be interesting to think about what's the kind of global structure that induces on the surface. So, let's try to draw a slightly more global picture. So if phi2 is meromorphic, with at least one pole of order at least 2, with only simple zeros, and some additional genericity condition, which I don't want to write right now, but sufficiently generic. Then the global picture is going to look like we've got a bunch of zeros and a bunch of poles. And then what happens is, if you look at a typical trajectory, so I'm calling them trajectories, but they're a leaf of this foliation. The leaves of the trajectories of the quadratic differential. So if you look at a kind of random trajectory, what it does is it'll travel around the surface for a while, but eventually it gets close to one of the singularities. And once it gets close, you see the local pictures here show you that it'll just be attracted to the singularity. And so topologically, it just starts at, if you follow it in either direction, you end up at a singularity. So you could draw it like this. And the nearby ones do the same thing. So there's some family of these things that look like that. And then there's another family here. Looks like this. One that looks like this, and so on. And then there are some special trajectories, and the special trajectories are the ones that at the zeros of the quadratic differential from one side or the other. So we could think of it in the following way. We start at the zero of the quadratic differential. We know that locally around the zero, there are these 3 trajectories that shoot out, and those will end up at a pole on the other end. So they look like this. So that's a picture of what the surface looks like, kind of as seen by this quadratic differential. You get this kind of decomposition into cells. Each cell is swept out by leaves that have the same initial and final singularity. So we got a kind of cell decomposition of C. And another way of thinking of that cell decomposition is that it corresponds to an ideal triangulation of the surface. So given this picture, I can make an ideal triangulation of the surface, namely each group of leaves I just associate with an edge. And so now you see, like in this picture, you see 2 faces of a triangulation. Has in its interior one of the zeros of this quadratic differential. So another way of thinking of this structure is that, having this quadratic differential produces this foliation, which produces in particular an ideal triangulation of the surface. Now, okay, so that's part of what we want to generalize to higher rank in this spectral network story. Okay, so maybe the last thing is, let's give the so in this picture you can see that the data of the ideal triangulation, knowing the ideal triangulation is more or less knowing these special leaves, the leaves that emanate from the zeros of the quadratic differential, the branch points. And so let's give those leaves a name. Let's say the critical graph of phi 2 and theta. We'll define that to be the union of the leaves that end on branch points. Okay, so that's a thing that's very well studied by people who work in the Teichmüller theory, the critical graph of a quadratic differential. And the spectral network that we're going to define is like the a candidate kind of higher rank analog of the critical graph of a quadratic differential. Okay. So that was the structure for n equals 2. Let's say a little bit, at least, about what these foliations look like in higher rank.
And a short question. For us, the higher rank is just higher order spectral equation, right?
Yeah, sorry. N, it's this number n that I had.
Yeah. So higher degree spectral curve, right?
Yeah, exactly.
Okay.
Yeah. For n equals 2, for n equals 2, everything that I tell you, at least today, is not in any way new. It's just the standard thing that you do with a quadratic differential. And I'm just reviewing it to show you how you recover it from this general picture.
Can I ask a question? What happens to this graph with the action of theta? I mean, does that change the incidence structure, or?
Yeah. So that'll be very important in the following story. So indeed, if you as you change the parameter theta, if you change it a little bit, then the topology of this picture doesn't change. In fact, let me see if I have a picture of this handy for you. Yeah, okay, I have an example of this. Can you see a little Mathematica notebook here?
Yes, we can.
Yes.
Okay. So this is a picture corresponding to a quadratic differential, which is a cubic polynomial, literally the polynomial z cubed minus 1. And I just plotted the critical graph of that quadratic differential. And so that corresponds to kind of the corresponding triangulation would be like a triangulation of a pentagon. Yeah, sorry, I guess I can't draw it directly onto here, but it's a pentagon. Here are the external 5, and then here are the 2 internal edges. And now you're asking, what happens when I change the parameter theta? So let's just see what happens. So when I change theta a little bit, the picture just kind of rotates continuously. But then there's a critical moment where something, where there's a trajectory that runs straight from one singularity into another, from one branch point into another. And at that moment, the topology of the thing suddenly changes. And so that would correspond to a flip of the triangulation. So yeah, that's one of the crucial phenomena in this story, which we won't talk about much today, but in the following lecture probably. So anyway, yeah, so things are kind of locally constant. Interesting moments when things change.
So does that mean that you have, I mean, if I were to forget the story of all of this apparatus of the quadratic differential and this associated branch surface, I mean, if I just start with a triangulation of the plane or of some surface, is there some kind of more immediate a way of thinking about this action of rotation?
Yeah, I think if you just start with the triangulation and nothing else, I don't think you can make the circle action with just that.
Well, let's say embedded triangulation. So I'm thinking of like some sort of critical triangulation, say with where I, you know, it's not just the combinatorial structure, but in, you know, where an embedded triangulation.
Even with the actual curve,
because what you're looking, what it looks like what's happening here is you're moving points, and then perhaps you're breaking some Delaunay condition, and that's why you're getting a flip, say. But you're somehow moving the points in some uniformly with this theta, and I'm wondering what this transformation is somehow.
Yeah, I think the short answer is I don't know how to set this up without using the kind of holomorphic apparatus. And I think that you probably can't, at least if you want to see precisely this sequence of flips, because there's another phenomenon where if I were to change this polynomial by moving the 0 on the right closer to the center. So in so doing, I wouldn't change this triangulation, but I would change the sequence of flips that it undergoes when I rotate is. So I think it's a little bit sensitive to the holomorphic data, but maybe we can think about that a little after.
Okay. Thank you.
Okay. Okay, so let me at least start to indicate what's the story for higher rank. So for that, we're going to use these. We're going to be using these. So now I got to try to draw some pictures of the foliations for when n is bigger than 2. So let's say n equals 3. So now remember, so we have this sigma twiddle, which is carrying a natural foliation, but which is a 6-to-1 cover of our base surface C. And the data that it was determined was a quadratic and cubic differential. But that's the data we have. We have a quadratic differential and a cubic differential on our surface. And given that, we had, well, first we had a 3-to-1 cover, which was the usual spectral curve. And then we built the 6-to-1 cover by taking pairs of sheets. And we have a foliation on the 6-to-1 cover. Suppose I project that foliation down to the base curve. What I'm going to see is, well, a priori, you would say locally I should see 6 foliations. But again, there's this Z2 action, which reduces it to just 3 unoriented foliations. So let's project the foliations. The foliation f theta from sigma twiddle to C. So in a neighborhood of a point which is not in the discriminant locus, what you'll see is, so before we saw just one foliation, now we're going to see 3 foliations. So 3 regular foliations. And so the topology of the picture will look something like this. And if I like, I could label the different foliations by where they came from on the cover. So, for example, the leaves going this way, I can orient and then label them, say with that orientation, they came from, say, they came from the 1-2 sheet of the cover. Then the foliations this way came from the 1-3 sheet, and the foliations this way. So now I have to be careful. Once I've done those 2, this one is determined. I think this is 3-2. So locally, the picture that I have on the curve is this picture of 3 distinct foliations intersecting with each other. That's the kind of generic picture that you see, at least topologically, although not. And then around a branch point, you have some pretty complicated mixing of the foliations. So I will not attempt to draw all of the foliations in a neighborhood of the branch point. But if you focus on just, so this branch point is carrying some transposition. 2 of the sheets of the covering are exchanging with each other. And if you just focus on that part of the foliation, in this case, as I've drawn it, the 1-2 part of the foliation, then you see a picture which is much like what you had in the n=2 example. You see a picture like that. And again, if I wanted, I could label them. I could orient. And then once I orient them, I can label them, say, this comes from the 1-2 sheet. Okay. So that's what the local picture of the foliations looks like, at least part of what the local structure of the foliations looks like. Okay, and now I want to make the kind of analog of the critical graph here. Okay, so I think I'll do this. In the notes, I gave a rather systematic presentation of it, but since the time is a little bit short, I think maybe what I'll give you now is the sort of short version of that, which is I'll give you the algorithm for constructing the object. So this is the object network. So call it W of theta and phi. It's constructed by, so let's assume sigma by simple, so simple ramification, smooth and simple ramification. So the spectral network is going to be some subset of the base, which is constructed by the following algorithm. And then maybe, yeah, so I'll just tell you that, and then I'll show you and it'll be for next time to convince you that it's an interesting object. So here's the practical matter. Sorry. So here's what you do. You begin at the branch points. You take the branch points of your covering, which may be here. And as we've seen in the picture just above here, at each branch point there are three leaves of the foliation, leaves of one of the foliations, which are.
Where are those branch points? In C?
Yes, in C, absolutely. So this is a picture on C. That's right. So these are the points above which the ramification happens. So for each one of those, there are three distinguished leaves of the foliation upstairs. But I'll draw the projection of those leaves back down to the base. And those are going to be part of the spectral network. So I'll take three leaves. These three special leaves emanating from each branch point. I guess again, as in the case of the quadratic differential, I'll call those the critical leaves. Maybe let's mark them here. So this picture is on C. So we first take the critical leaves emanating from each branch point. And so in the case of a quadratic differential, that was the critical graph you get by just taking the critical leaves and do nothing else. But in the general situation, n greater than 2, there's a phenomenon which can occur, which did not occur in the story of a quadratic differential. Namely, these leaves, their projections down to the base could intersect. In the n equals 2 case, that couldn't happen because the projections down were still leaves of a globally defined foliation. But now, as we've seen, these foliations can intersect. Leaves of these foliations can intersect when they're projected down to the base. And when they intersect, we include additional half leaves. I guess these you might also call, well, here it naturally ends somewhere, so you don't call it a half leaf. But now, whenever we have two leaves whose projections to the base intersect, we're going to add additional half leaves whenever projections of leaves that were included intersect. According to the following rule, so each of the leaves, so the foliation is living on this root cover, so each leaf is coming with a label by a pair of sheets of sigma, right? So it's labeled, say, IJ. That's the label that labels a sheet of this cover. We have another leaf, and suppose that that other leaf is labeled JK with one index in common, so IJ and JK. In that situation, when they intersect, we include an additional half leaf. So we say the spectral network in that case will include not just the two original leaves, but also an additional half leaf, which starts at the intersection point between the projections and lies on the IK sheet. So the picture is like that. And so whenever I have an intersection like this, the potential to create a new leaf, a new half leaf, which then also travels around the surface, and it may intersect with other ones. And every time they intersect, if they intersect in this pattern, IJ and JK, then you generate a new one. And you continue that process. You could say, if you like, you take the smallest collection of leaves that's under that process. But in practice, what you do is you just kind of iteratively, every time you add one, you check whether it intersects with all the previous ones. And if it does, then they give birth to new ones and so on. Okay. Yeah, I wrote a slightly sharper version of this in the notes, but I think maybe for our present purposes, that's enough. And I think the main thing is to show you some pictures of object can look like.
Sorry, Andrew, just to clarify. So IJ is the same as JI, or it's different?
IJ, so right, so IJ is not the same as
So it will change orientation, right?
Right, it would reverse the orientation, right? So when I draw it with an orientation, then the absolute label matters. It matters that IJ.
So when you consider the intersection IJ and JK, you want them exactly in this order, like IJ and JK. So IJ and KJ won't intersect as you.
Well, they can intersect, but they don't give birth to anything new. So that's right. So so if we had an intersection like this between IJ and IK, that's fine. That intersection can happen, but
Oh, you.
yeah.
Screen sharing.
Yeah. Just a moment. Yeah, there it is. Have you got it there?
Yeah.
Yeah. Are you going to repeat everything before?
I wasn't planning on it. Yeah, so when they intersect in any pattern other than IJ and JK, that intersection can occur, but when it does, we don't create a new trajectory.
Okay.
But the only time when we create a new trajectory is exactly this IJ JK situation. Yeah, so in general, I guess I should say, well, all right, let's just leave it at that.
Andy,
Yeah.
can I follow up? So like Misha said, this would be, so KI will be the same curve, but with the orientation reversed, but then you will create a new curve, right?
Right. That's right. So they come with a natural orientation. So the intersection had been like, so you're absolutely right. If the intersection had been like this, where I had an IJ, it would have created a new curve going out in this direction, by the way.
But why is this curve not visible from the picture before?
I think the key thing is that in this construction, the orientation, they're born on the branch point. Said otherwise, they really live on this sigma twiddle. On sigma twiddle, they live on a definite sheet with a definite orientation. So it's true that the projection looks the same as the projection of a curve coming the other way on the other sheet, but they really carry a definite label. They're in a specific place on sigma twiddle.
So
okay, I see.
Correct understanding that you have to draw all this spectral network on sigma twiddle, and then it's real intersection in sigma twiddle.
And then say that again.
I said that, well, the first picture different from the second one because you consider this picture lifted to sigma twiddle, and then IJ intersect on sigma twiddle, and IJ.
No, that's the tricky thing. The intersection is not there on sigma twiddle. The intersection is really the intersection of the projections, right? This IJ and JK, they live on absolutely different sheets of sigma twiddle.
Okay.
Right? It's not that they intersect on sigma twiddle in one case and not in the other.
Okay.
In both cases, they do not intersect on sigma twiddle. But nevertheless, you use the information of where exactly they sit on sigma twiddle to tell you whether you're going to generate this extra thing or not.
Yeah, sorry.
Andy, I'm sorry, I don't understand something really basic. So these trajectories that you've been drawing, right? There are critical leaves of the foliations. How do they give rise to something new when they intersect? So
well, right. So
are these IKs?
So I mean, that's something I'm going to have to justify in the future, you know, to convince you that this is a useful and interesting construction. So far, I didn't give you a motivation for doing that, and that I guess will be the next time. Right now, all I'm hoping to convince you is that there's a well-defined procedure, and that well-defined procedure just is that when two things intersect, they create a third one.
But this procedure is combinatorial. It's not even I mean, yeah, it's just a combinatorial procedure for now. It's, how to say, like the angle at which the IK emanates is not even there yet, right?
Oh no, that's absolutely determined. That's absolutely determined because the IK thing is a leaf of this foliation.
Oh, I see. Okay, yeah, I got it. Yeah.
Yeah. So once you specify the initial point, that leaf is completely determined. That half leaf is completely determined.
Oh, I see. I see.
Andy, can I follow up? So the point from which IK emanates is it like a pole of the form?
No, it's an absolutely of the with respect to all the structures that we've talked about before. There's nothing special about that point that can be detected locally. The only special thing about it is that it happens to be the intersection of these trajectories, which came from completely, their origin was somewhere else. So absolutely, this happens at a totally generic point in the middle of the surface.
Oh, okay. But I thought you mentioned that the leaves can only terminate at poles or like.
Well, that's right. This is not the end of the leaf. That's why I called it a half leaf.
I see. I see.
That leaf absolutely could be continued in the other direction. And indeed, in some aspects of this theory, some people do like to continue it in the other direction. But for my purpose, I don't want to do that. But absolutely, that leaf could have been continued, but by definition, the spectrum only includes one side of it. Okay, this is great.
Also, I have a question. Is the final picture finite? Do you have finite number of vertices in that network? If you continue this algorithm, will it stop somewhere? do you have finite number of intersections?
These leaves forever. Sorry, the connection wasn't very good.
I think I can repeat. Maxim asks if this procedure is finite, if you stop after a finite number of steps. Or you can add...
It's right, good. So in general, the collection of trajectories produced by this procedure is infinite. There are some examples in which the collection is finite, and those are particularly nice to look at. And so maybe I can draw you a few pictures. But that's right. In general, this thing seems very unpleasantly infinite, and we don't have a lot of control over it. And that's one of the biggest problems in this theory, I think, is to get some control over this this process. But let me show you a few simple pictures just to get a handle on what we're talking about here. Well, let me show you one anyway. I'll just sketch it for you. So let's talk about the example where this is literally the complex plane. Or I guess I could say CP1. And let's take n to be 3. And let's take, so I'm going to give a meromorphic quadratic and cubic differential. So phi1 is 0 again. What does that mean? It means a polynomial, right? So, and for phi2, I'll just -1 times dz squared. And then for phi3, the cubic differential, I'll take z dz cubed. And let me just draw what the picture comes out to be in that case. So here's the picture at, I think this is the picture at theta equals pi over 2. And I'm going to draw it by hand just so I can label all the objects. So first of all, in this case, the discriminant locus consists of two points. That's because in this case, the discriminant locus is literally, so we're studying the spectral curve, which in this case is just given by the by a cubic equation, right? It's y cubed plus well, minus y cubed minus y plus z equals 0. That's the spectral curve. And so the discriminant locus is literally the zeros of the discriminant of this cubic polynomial. The discriminant is, I guess, 4z squared minus 27. So it has two zeros. There are the two zeros. And then the branching structure branch cuts like this. So I got it labeled. So this one is sheets 1 and 2 exchange, and this one sheets 2 and 3. And then what happens for the trajectories is, so each one of those emits 3 trajectories. And those trajectories, now in this simple polynomial example, the trajectories tend to be attracted to infinity. This is big singularity to infinity. And so that, the trajectories tend to go there. And so if I label them, those 3 go out like this. And then here go 3 more. And this guy.
Andy, is one of the 2 ones 1, 2? Because there seems to be a contradiction.
Yeah. Yes, this should be 1, 2. So this should be 2, 3. Oh yeah, it's okay. This is 3, 2. This is 2, 3. of type 1, 3. And then here, likewise, these are 3, 2, and 2, 1. And so they generate a new one. There's a total of 8 trajectories in the picture. Okay. But in general, it's that you don't always have this finiteness. Okay. So I think maybe that's a reasonable place to stop. So what have I managed to do? I managed to introduce all the players in the story and to define this object called spectral network. If you look in the notes, you'll see a little more, slightly more systematic construction where this algorithm appears as the way of computing it rather than the definition. But ultimately, this is the object. And then, so, begging your indulgence, if you come back for the next one, I will try to tell you some uses of this object, why this is why this seems to be an important object. But I think that's probably a good place to stop for now.
Thank you. So, may I ask? So, I understand that you promised to tell the use like next time, but can you say like few sentences about right?
Okay, let me say one.
For motivation, yeah.
Yes, you're right. Let me say one motivation. Okay, so. So the data that we had here of a bunch of differentials, it defines a spectral curve, but it's also what you would need if you wanted to write down some kind of ordinary differential equation curve. So, like for example, for this this example above that I drew here would correspond to the equation d by dz cubed. Let's write h bar cubed d by dz cubed plus, well, phi 2 of z d by dz plus phi 3 of z psi equals 0. Suppose you want to study that differential equation, particularly suppose you want to like calculate the well, this is in the plane, so it doesn't have exactly monodromy. So in this case, it would be like, suppose you want to calculate the Stokes data of this ordinary differential equation. Or in similar examples on a compact surface, it would be you want to calculate the monodromy of this differential equation. If you want to do that, it turns out that one of the basic tools is this machine called the WKB method for constructing local solutions of the ODE. And you build them by Borel resummation of some formal series in H bar. And as it turns out, in the rank 2 case, by now the theory is pretty well understood. And what it turns out is that the way you build these local solutions, by this Borel summation, it works exactly in the complement of spectral network. Trying to build a solution of the equation, it turns out you can't build it globally. You can build it away from some certain subset, and that subset is exactly it's conjectured, although I think it's not quite proved yet, but there's a lot of evidence that that in the higher rank situations, the Borel summation will work exactly away from this diagram that I've drawn here, the spectral network. So in other words, these spectral networks would appear automatically from the kind of trying to construct by singular perturbation theory in H-bar, trying to construct solutions of this equation. So that's kind of one place where they would come up. I don't know. Should I say more places where they come up?
No, I think I'm happy for now. Any other questions?
I have a short question. Could you recall, please, what's the abbreviation WKB stands for?
Yeah. Oh, but I'm afraid I might not spell their names correctly. So it's like Wenzel, Kramers, it's the name of some physicists who were using this method to study differential equations. I think it's also sometimes called like the Leville-Green method. But yeah, there's a big community that studies this method under the name WKB or sometimes exact WKB.
It's called VKB, VKB по-русски, in Russian. It's called the same letter in Russian.
And sorry, I have two really short questions. So did you say that in SL2 this is known that this WKB works precisely outside this locus, but in high rank it's just a conjecture?
That's right.
And second question is, could you remind what was the rationale for calling those emanating rays 1-2 versus 2-1?
You mean the ones that first come out of the singularity?
Yeah, of the singularities, exactly.
Well, maybe the fastest way of saying it is this: at the singularity, so we have these three distinguished trajectories, right?
Right.
Now, as we've kind of said, if you just draw that trajectory without an orientation, you haven't quite determined which sheet of the covering it comes from. But as soon as you fix an orientation, that determines exactly which sheet it comes from, because the foliation upstairs is oriented.
Mm-hmm.
So the way the logic goes is we fix the orientation to be the outward going orientation, coming outward from the singularity. Having done that, that determines exactly which sheet of sigma twiddle it lies on.
But when you have two rays, two trajectories, both labeled 1-2, does that mean that they come from the same thing in sigma twiddle?
It means they're on the same sheet. Yeah, you want me to draw the picture on the double cover? Maybe it's useful to draw the picture on the double on sigma twiddle. So on sigma twiddle, the picture was. So then it's this thing with six sectors, right?
Uh-huh.
And then so on sigma twiddle, what we have is just the oriented foliation like this.
Oh, I see. Okay, got it.
And we're just taking that picture and pushing it down to.
Yeah, got it. Thanks so much. Yeah. Mm-hmm.
Okay. Any more questions? If not, I think it's time to wrap up. So let's thank Andy again, and hope see you next week.
That's good.
Thank you.
Максим, а вы можете меня спрашивали про запись. Well, is it possible to share record link or something? I was asked several people if it's possible.
To share what?
Recording.
Oh, I guess so, yeah.